Okay, gang, welcome to CS470 Computer Graphics. And today, what we're going to be doing is we're going to look at a number of things. Why don't I go ahead and let's see. Well, the first thing we're going to do is we're going to talk about display technology for a little bit. Just because eventually everything ends up being displayed. So I guess we should say a few words about that. Then we're going to move on and talk about how polygons are represented in computer graphics. And then we will talk about projection, and maybe we'll get to the drawing window as well. But that's kind of what I have set out for today. Displays, polygons, projection, and conversion to display coordinates. We'll see how far we actually get. So if you, with that introduction, let me move over here and bring up my lecture notes. So, I want to share it. I'll get there eventually. Sorry, it takes me a while. Okay. So you should be seeing my lecture notes here. So we're going to talk just a little bit briefly about display devices, and the reason for that is even though we're going to be focused on three-dimensional computer graphics, eventually those 3D graphics have to be converted into 2D images on flat displays. Sometimes some of the screens are curved now, but they're essentially all flat. We don't have any kind of holographic displays, and there's a few little tricks that have been out there. And in fact, some of the tricks that people think of as new holographic are based on Pepper's Ghost, which dates back to the 1800s. So sometimes new things are actually very old. But most everything that we look at these days, you know, are from our TVs to our phones to our tablets to our laptops. We're all looking at flat displays. And so even, you know, you might say, well, what about VR, right? Yeah, that's three-dimensional. Well, VR, basically, it's two flat images rendered from slightly different perspectives to match each eye, and that allows you to appear to have three-dimensional worlds, but really you're just looking at two flat images is all you're looking at there. So anyway, everything we're going to do is we're going to end up generating flat images. The display devices that are out today include LCDs, liquid crystal displays, OLEDs, organic light-emitting diodes. You might still find a plasma display somewhere. But basically all of these technologies these days are built to light up lots of very tiny pixels. A pixel, the word actually means picture element. Picture element is where the word comes from, and it's just a dot. And the tinier the dot and the more dots you have, generally the better, the quality of the image. Now, it's interesting because those of you who actually, since you're all on your computers and you can have multiple windows open, why don't you go into Google and type in George Seurat. Don't ask me to spell Seurat. Maybe somebody can spell it in chat. But Seurat was a painter, a French painter from the late 1800s. And he had an interesting idea that he explored. He took it to its illogical conclusion, I guess you might say, by drawing these giant paintings that consisted of only a small number of colors, like 3 or 4 colors. And his idea was that if you draw dots of colors close enough together, that your eye will blend the colors. And so you can get different shades of color from just a couple of base colors. And today we build all of the displays, the color display that you're looking at in front of you that has my image on it and the Stargate in the background and everything else that's on your screen. You really only, the technology is really only producing 3 colors, red, green, and blue, and it's producing them in different intensities. But because you have the red, greens, and blues right next to each other and they're teeny, teeny, tiny, your eye combines those together to see colors. So, you know, there is no yellow pixels. But if you look at my image, you can see that the Stargate, some of the chevrons are lit up in kind of a reddish gold color. There are no pixel colors for that, but it's just that the little red, greens, and blues are so close together that they build into that. So that's the way displays work these days. If you go back about 15 or 20 years, even 15 years ago, to say 2005, there was that's about the time that CRTs, or cathode ray tubes, were being replaced by flat screen displays. And it took a while. It took probably 5 years or so, maybe 10 for the transfer of the technology to take place. In the late 90s, pretty much everything was CRTs, but like I said, by around 2005, pretty much displays had moved to flat screen LCDs. But the CRTs, or the cathode ray tubes, are interesting from a historical perspective. I don't have time to go into them in any depth, but that was the display technology that ruled for over half a century. So, you know, flat screen displays commonly for TVs and stuff like that have been around, you know, for 15 or 20 years. The cathode ray tube, the TV tube, was around for more like 50. That's pretty interesting. Early CRTs were vector devices, and they were later replaced by raster devices. What do I mean by that? Well, CRTs were interesting. It's funny, you know, we think that our technology becomes more complicated, but in a sense, actually, many things become simpler as our technology progresses. Like, you know, I mentioned this to a lot of people. I own a Tesla, right, an electric car. Well, even though Teslas are kind of like first-generation electric cars, they're more reliable, need far less maintenance than a normal ICE engine, internal combustion engine vehicle. And if you look at how it works, there's a battery that's hooked up to a motor, an electric motor, and that's basically the car, a big battery and an electric motor. But if you look at like an ICE, you know, car, an internal combustion engine, you know, it's this complicated Rube Goldberg thing with these pistons and these, you know, camshafts and these, you know, valves that open and close and these little explosions that are going on inside I mean, it's so complicated. If you describe it to somebody, they might say, I don't think that internal combustion engine's ever going to work. I mean, yeah, it sounds good on paper, but there's so many, all these explosions that have to be perfectly timed, and I don't think so. So things get simpler. The same thing with displays. You know, now they're just solid state matrices, rectangular matrices of very large numbers of pixels, where each pixel will have a red, green, and blue component to it. And so, they're lined up in rows and columns. It's what could be simpler. Nothing moves. It's all solid state. Well, if you look at the early, if you go back to cathode ray tubes, it was actually a giant vacuum tube that had an electron gun that shot electrons, literally a stream of electrons, towards the screen. And on that screen, there was, I'm going to make an image bigger. On that screen, there was phosphorus. And so where the electrons hit the phosphor, the people would be over here, you'd get a glowing dot on the screen. So the electron gun is spitting out these electrons, and they're hitting the screen, and the person in front of it sees the dot. And you might say, well, that's a dot. How do you get an image out of that? Well, in the early days, well, actually always, what happened is there were electromagnets on both sides of the electron stream and on the top and the bottom of the electron stream. And by changing the intensity of these electromagnets, you could bend the electron direction of the stream. So you could stream it in one way and stream it another. And by doing that, by changing the intensity of the magnetic coils around the electron flow, electrons are what, negatively charged? So because of that, they're attracted by electromagnets. So because of that, you could, like, say, if I wanted to draw out, I'll turn it like this. If I wanted to draw out a triangle, I might, have the beam do something like that. Draw a triangle over and over and over, and over here, I would see the triangle that was being drawn. That was called a vector display, because you're drawing lines by tracing them out, by changing the electromagnet. That was early computer graphics, and you could only get line drawings out of that. You couldn't get detailed images out of it. You may have seen something similar to this if you've ever seen a laser show. Lasers where, like, sometimes in the sky or on a big screen, they'll be drawing out patterns. But if the pattern gets really complicated, you can kind of see it being redrawn. And that was the same problem that vector displays had, because as you're just tracing an image over and over and over, and either it begins to fade before it gets completely redrawn, or if you're trying to do movement, you get this smearing effect. But in the 1940s and 50s, vector graphics were pretty common. Later on, we got to what were called raster graphics. Raster graphics were interesting in that what they did is they question, can you see my mouse pointer? Yes or no? Can you guys see my mouse pointer?
You're not screen sharing right now.
No, that's true. I didn't realize that you didn't get to see it if I wasn't screen sharing. Hold on. I will go back to share screen, and I will go back to my lecture notes here. So you can see my mousey now, right? Yes.
Yeah.
Okay. So we've already described how vector graphics work. It would, if I wanted a triangle, I would draw a triangle over and over and over by changing the electromagnets. But you couldn't get very complicated images. The next thing after vector graphics were raster graphics. And in raster graphics, the technology had progressed for a while. And so what you could do is you could draw a line, and then you would draw another line, and then you would come back and you would draw another line. So basically, you would build up an image line by line. And in early, in TVs until they about 5 years ago cut off the old, or maybe it was 10, they cut off the old analog television format. It was 640 approximately pixels by 480 lines. So your image was built up of dots, where you could have 640 dots across and 480 lines or dots downward. And so that's what the electron gun, the electromagnets in the electron guns would scan line, and then come back and scan another scan line, and then come back and scan another scan line. You might say, well, if you're doing that, aren't you just going to get a white screen? And the answer is yes. But what would happen is also with that, the electron gun, would, as it spits out electrons, would turn on and off very rapidly. So if I wanted a dot here, I would turn on the electron gun as it was passing this spot, as the electromagnets were passing this spot on the screen, and I'd spit out a dot. And then if I wanted all of this to be black, the electron gun would be off. And if I wanted, some white dots here, it would turn back on again. And so that's basically the way TVs worked. But the image quality was pretty crappy. And it was even crappier than I'm describing, because I'm saying it's 640 by 480, but really it was 640 by 480 interlaced, which meant that it would draw one field of lines, and then on the next pass it would come back and it would fill in the lines between them. And so since televisions worked at 60 hertz, because that's the frequency that our alternating current in our houses use, you would get half of a frame or half of an image on one pass, and the other half of the image on the next pass. And since it would take two passes to do that, and you had 60 hertz, you could get 30 full images a second out of it. But it was actually 60 passes where you draw, instead of 480, you draw 240 lines on one pass and 240 lines on the next pass, interlaced together to draw an image. See how complicated all that is? But why did they do that? Well, they did that because it was very expensive to try to build something that could oscillate, right, that fast. And you had this electron gun, and you had to be manipulating your electromagnets and all that sort of stuff. So it was like crazy complicated. But it worked. And it was basically televisions for half a century. From, say, when televisions first came out in the early 1950s to the early 2000s. So you're saying it could draw a whole screen in one pulse of the AC from the wall? Alternating current alternates, and it's at 60 hertz. So that's 60 cycles a second. And the TV in one of those cycles would make a pass down the screen, okay, drawing every other line. And then in the next pulse, it would make another pass down the screen, filling in the lines it missed. And so when in a second, right, since there are 60 cycles in a second, 60 hertz, it could draw 30 full images. So it doesn't draw a screen in a pulse. It draws a screen every. It takes two cycles to do that. So every 30th of a second, it would draw a full image. And 30 frames a second is enough that you get pretty smooth movement. And because you were filling in those lines quickly enough, you wouldn't notice any. You wouldn't. It looked like solid images that were moving because it was too fast for your eyes to see the images being built up. So it worked. We talked about 640 by 480 as a resolution, but probably the first resolution you guys might be familiar with is 1024 by 768. That was a computer resolution that was pretty common a while back, and I haven't looked at what my laptop is set to because I'm old and blind and need things to be a little bigger. I wouldn't be surprised if my laptop screen is running at 1024 by 768 or something close to that. It's interesting. We were talking about pixels. So if you've got a horizontal resolution of 1,024 dots, and you have 768 lines, where each line has 1,024 dots, okay? You multiply those numbers together times how much storage you're using per pixel, and that gives you how much memory it takes to hold an image. And you will see in 1024 by 768, it's a little over 2 megabytes, about 2.5 megabytes, okay, for one image. And now you're beginning to see why video takes up so much space when you start storing off videos. Why 3 bytes per pixel? That goes back to how we did color. I talk about color down here. In color, basically what you do is you have, like I said, you'll have a red subpixel, a green subpixel, and a blue subpixel, RGB, red, green, blue. You have to be able to set the intensity of those subpixels, and basically what we use is 8 bits for each subpixel to store its color value. So you have essentially 256 levels of red, 256 levels of green, and 256 levels of blue. That's called 24-bit color because you're using 8 bits for red, 8 bits for green, and 8 bits for blue. That gives you about 16.8 million colors. This standard hasn't changed in well over 20 years. And the reason why it hasn't changed, why hasn't it gotten better? Doesn't everything get better in computing? Well, basically, your eye can't see more than 16.8 million colors. So we could add more bits, but it's not going to help because we're at the limit or beyond the limit of what a human can see. Sometimes though you'll see an extra byte. Instead of 3 bytes, you might have 4 bytes. Somebody asked a question in chat about what about RGBY, right? Well, you could have another component for pixels. Sometimes the third component is used for transparency. Sometimes it's used for additional things that can marginally improve an image. But really, if you've got 256 levels of red, green, and blue, you're pretty much at the limit of what a human can see. And of course, it's going to cost you a third more if you add a 4th byte. You're up to over 3 megabytes at that point. So an interesting thing would happen if you took 1024 and divided it by 768, you would see that that's a 4:3 aspect ratio. And why is that? Well, because old televisions and computer monitors back in the day were almost square. They were a little bit rectangular, a little wider than they were tall, but not by very much. So if you watch like if you go and you watch like an original Star Trek episode or something from the 1960s on your TV, you'll notice that there are black bars on the right and left side of the image. Either that or they've squished the image and distorted it so that it fits your TV screen, but normally they just leave the black bars on either side. And the reason for that is that your display is a 16:9 display. That's its aspect ratio. It's much wider than the old 4:3 displays. And so if you're going to show material that was generated at 4x3, well, you either have to stretch it, which makes it look kind of funny, or you have to clip out parts of it, which is not a good solution, or you just you show the whole image and leave black bars on the sides. So HD, high definition, is the first HD standard was like 1920 by 1080. And if you took 1920 over 1080, you'd see that that's a 16 by 9 aspect ratio. And again, you can have 3 bytes per pixel, which is normally what's done, or in some cases you have 4. But you see that you're getting now one HD image is over 6 megabytes. And if you add that Y, or you add some transparency level, now you're at over 8 megabytes for one still image. And remember, you're going to want 30 frames a second. You greedy gamers want 60 frames a second, right? You guys are such prima donnas. You guys get upset if the frame rate falls below 60, like you can really see it. Ha ha ha. But you think you can, so you can, I guess. But no. So start thinking about that. I want an HD image. It's going to take me 6 megabytes worth of memory to hold that image. Or if you're thinking about you're generating an image, you have to generate 6 megabytes of data for one image. Now multiply that by 30, right? So what, you add a 0, so that gives us 60, and then multiply by 3, right? So that's 180 megabytes worth of information that you have to generate each second for 30 frames of imagery a second. And then you start thinking about that's 1 second. So, you think about a movie that lasts for 2 hours. You think about how much data is actually there. It's amazing. And that's just plain old vanilla HD. If you go to 4K, and 4K is last year's standard, well, now, but that's generally, they're different standards, but 3,840 by 2,160. Again, these are 16 by 9, but now you're looking at 33 megabytes. Then you got to generate per image, and you got to do that, either 30 or 60 times a second, and now you can begin to see why graphics hardware needs to be so blindingly fast. Eric, what is this 144 frames per second? That's crazy talk. Crazy talk. You can't see that. No way. And Eric is saying, yes, he can see that. You can see 144 frames a second. Okay. Some people are like, 240. You guys are insane. Okay. All right. You can have your 144 frames a second, I guess. I would much rather have a much higher resolution image, quite frankly, than those crazy high frame rates. And I guess what you're saying is there's less flicker and it's smoother, right? I've gotten into religious territory with Eric here. So and Ross is typing up that he's got 144 hertz on 1920. But yeah, okay. All right, guys. Calm down. Calm down. But you realize what you're doing when you're demanding those frame rates, right? Because nothing's free. So, and some of you guys, sacrifice resolution for that. And for me, I think that's silly. If I have to choose, I would choose 30 to 60 frames a second and a much higher resolution. But it's all, different people budget their money in different ways. And, some things are, a fancy car is important to some people and a bigger house is important to other people. So it's what you want, I guess, right? We can all live together. Cats and dogs all living together. Okay, so that's basically, we covered standard TV definition. We talked about interlace versus progressive. Progressive is when you draw every line on the screen per image. That's why you'll sometimes see an I or a P, not so much anymore, but you go back 5 years, 6, 7 years, you'll see sometimes the TV will talk about 1080i or 1080p. Well, that little I and P means a lot, because if there's an I there, it's doing half the work that a P is doing, because it's only drawing half the image per frame. So that's extremely important there. But any case. So that's, and then I talk about refresh rates there. And you guys with your 144 frames, remember that movies are 24 frames a second. And I don't see you guys throwing up, when you watch, Captain America. Filmed movies they're actually 48 frames a second, because they show every image twice. Okay. And you're saying movies have an inherent motion blur added in, though. Well, maybe, no, sort of. Modern TVs will interpolate and generate more frames, and will up-convert a 24-frame movie source to 30 or 60 frames. And some purists hate that, because it makes movies look like they were shot on videotape rather than a movie. You lose the subtle feel of a movie when you up-convert it like that. It looks, to some people, it looks cheap, because it looks too sharp, I guess you might say. Soap opera, film format to soap opera format. That's exactly it, Blake. It's not so bad on newer TVs, but if you go back even 5 years, that technology, I remember the first time I saw a TV like that, and actually my roommate had that on his TV in his bedroom, and I didn't on the big screen in the den. And I remember walking, I guess we were watching the same thing, and I walked into his bedroom and I looked at his TV set and I said, "What is wrong with your TV?" And he's like, "What do you mean? There's nothing wrong with my TV. It's a brand new TV." I'm like, "Yeah, but everything looks weird." And that's the deal. The up sampling on it could make things look weird. Anyway, we've talked way too long on this topic. Let me move forward. Okay? Any questions before I move forward on this? Okay. All righty. So I do see that some of you do like the lower frame rate with the motion blur from movies. That's nice that some people can still see the difference who are under 30. Okay, polygons. So we talked about display technology for a while, but what we're really going to be doing is we are going to be drawing polygons in almost all of computer graphics. When we get to ray tracing, we're going to leave polygons behind, just to simplify some calculations. But by and large, almost all of computer graphics, especially 3D computer graphics, objects are built out of polygons. What's a polygon? A polygon is a flat, multi-sided figure, like a triangle or a square. So this is a polygon. It's a triangle. This is a polygon. It's a rectangle. Actually, this rectangle is a square. In mathematics, depending on how you define this thing, you might call it a polygon. We tend not to allow these sorts of polygons here. It's not that it has 1, 2, 3, 4 lines. That's not the problem. The problem is the lines cross. And generally, we don't allow that to be a polygon. So in this class, this wouldn't be a polygon. Now, you might say, but I could draw this figure. It's 2 triangles. And yeah, if you wanted to draw this figure, you could. You could draw it using 2 polygons, 2 triangles. that's fine. But what I'm saying is, as one thing, where you draw a line, you draw a cross line, you draw a bottom line, you draw a back cross line. That's not allowed. That's not a polygon as we're defining it in this class. So from these very simple polygons, these flat multi-sided figures, you generally have a very, very large number of very, very small polygons, and that's how you build up a 3D computer graphics model. Now, to keep things even simpler, most systems these days limit themselves to just triangles. In this class, we'll mainly use triangles, but sometimes, occasionally, we might use a rectangle. If you're trying to generate code and make it really, really fast, if every polygon is a triangle, you can hard code things to expect that there are three and exactly three vertices, and you can't get, with a three vertex triangle, you can never get crossing edges. So there are, if you limit yourself to three edges and a closed figure, a triangle, you don't have to worry about this crossing over crap that can cause problems for various algorithms. So if everything is a triangle, then you can set up your system to process triangles and make it blindingly fast, which of course you need for you people who want 144 frames a second. Sorry, which you need for high resolution and high frame rates. I'm just not going to let go of that 144 frames a second. See, I learn something every time I teach this class. I learn something new, and so I guess 144 frames per second is now the new thing that you have to have. Okay, so back in my day, we had 24 frames a second, and we liked it. I don't know. Okay, so let's see. So we talked about triangles. Normally, we limit ourselves to triangles. Note that arbitrary polygons can be constructed from multiple triangles, as I noted here. While this wouldn't be a valid polygon, you could certainly build this image using two triangles. And so any arbitrary polygon can be built out of multiple triangles. So 3D objects are 3D. They exist in 3D space. Polygons, however, are actually flat. But you can build 3D objects because you can put the polygons at different angles. So let's say that you wanted to build a pyramid. So what I have here in the middle of the screen is I have a pyramid. Now, the screen you're looking at is flat. The piece of virtual paper that I virtually drew on is flat. So I cannot actually show you a true pyramid, which is a three-dimensional object. But I can show you a graphical representation of a pyramid. This pyramid is called a wireframe drawing. I did draw the back base in slight gray to show you that if you were rendering this pyramid using solids rather than just edges, you wouldn't be able to see this back line here. It wouldn't be visible. But if you're doing a wireframe, which is what we're starting with, we're starting with wireframe objects, you would be able to see all of these, and this wouldn't be gray. The back line would be drawn just as solid as the front line. There'd be no difference. Okay? So what's a object, a 3D object, and how can it be set up in a computer? Well, a 3D object, this pyramid is a 3D object. This 3D object consists of 4 triangles. The front triangle, the back triangle, the left triangle, and the right triangle. So 4 triangles plus, don't forget, a base. Okay, the bottom of this thing is the base. So it's 4 triangles and 1 rectangle is how this thing is set up. So An object, a 3D object, consists of some number of polygons, right? Mostly in computer graphic systems, we use triangles. You could use rectangles too. I chose to use 4 triangles and 1 rectangle. The rectangle is actually a square. What if I didn't want to use rectangles? What if I wanted to limit ourselves to triangles only? How could I draw this pyramid? What would I need to do? Anybody, go on audio and answer.
2 triangles for the base.
Okay, so I could use 2 triangles for the base. I could draw a triangle with a diagonal that went like this, and that would be 1 triangle. And then I could draw another triangle like that. So you might say, well, wouldn't there be a line here, Mike? Or I could have done it the other way where the line went this way, right? Depending on how I set up my triangles. That's true, there would be, but you don't always have to draw edges, so you could turn edge drawing off there so it didn't show up, right? So sometimes you can set edges to be visible or invisible depending on different stuff. Or you could just live with the triangle line there on the base of your pyramid. Okay, also too, I named this front, I named this guy back, I named this guy left, I named this guy right, I named this guy bottom. Those names are arbitrary, and clearly what's the front depends on the orientation of the pyramid. I mean, after all, I could potentially rotate that pyramid by, by 45 degrees. I can't do that here because it's a static image. But if I did that, there wouldn't really be a front, right? Because there'd be like 2 fronts. So if I move this thing so this side and this side, so that this edge here was facing me, right? You would see these 2 triangles is what you would see. So there wouldn't be a front face in that case. There would be 2 front faces, the left front face and the right front face, and there'd be 2 back faces, the back left and the back right, if you see what I'm saying. Usually I forgot to grab it from the office, but I have a little physical 3D triangle or physical 3D pyramid that makes some of these things easier to show off, but I don't got it at home with me. Okay, so here's another big important idea. All of the equations, pretty much, that we cover in this class are going to be linear equations. A linear equation is an equation that translates straight lines to straight lines. And that is going to be a godsend, because if we wanted to do something with this pyramid, like rotate it or move it, translate it or scale it, make it bigger or make it smaller, if we wanted to do any kind of operations on this puppy, you have to say, well, what do you do the operations on? Well, it turns out you can do the operations on just the vertices of the polygon, or sorry, of the vertices of the object. And then if you remember how your polygons are structured, you can redraw the object at its new spot. So it's not like every single dot of every single line has to be, let's say, moved. You could just move the vertices and then draw lines between those vertices in their new location, and you'd get exactly the same object. You'd get exactly the same as if you had done the work of moving every single pixel. So that's one of the reasons why we use polygons is you only really have to worry about, once you've set up the polygon structure, you really only have to worry about the vertices. So we've named our vertices A, or apex, and then our vertices for the base, B1, B2, B3, and B4, right? So that's 5 vertices. And these 5 vertices are used by the 1, 2, 3, 4 triangles and the base. So in this case, we ended up with 5 objects and 5 vertices, but that's not always the case. If we had used just triangles, remember, we would have had 6 triangles. We would still only have 5 vertices the apex and the 4 vertices on the base. So how is a polygon stored inside the computer? Because you guys in our first assignment, actually, you're going to be working with essentially this object, a pyramid. So how are you going to store the pyramid in the computer? Well, your pyramid will be, any object is really defined in a hierarchical manner. And our pyramid is an object that consists of a collection of 5 polygon objects, as we've talked about: front, back, left, right, base. The order of these polygons doesn't really matter. If you draw all 5 of them, you will end up with the same image, regardless of if I drew this one, and then I drew this one, and then I drew the front, and then I drew the back, and then I drew the base, or if I drew the base, and then I drew, it doesn't matter the order that you draw the polygons in, you still get the same image. Okay? Does that make sense? So that's why I say a pyramid object is a collection of 5 polygons. I'm using the word collection to emphasize the order of the polygons don't matter. Okay, but then you have to store the polygons, because how do I represent front and back and left and right and base, right? Well, you represent a polygon normally, one common way, is as a list of vertices. Notice I'm using the word list because the order is important. As a list of vertices specified in clockwise order when viewed from the outside. Now, you might say, why does the order matter? Couldn't I go A, B4, B1 here, and next time go A, B1, B4? As long as I connect everything back together, I should get exactly the same shape, right? And that's true. You would get exactly the same triangle, the same front-facing triangle, whether you went A, B1, B4, A, or A, B4, B1, A. Either way, you're going to get the same thing. But it's important for future stuff that we're going to do that you define all of your polygons consistently when viewing that polygon from the outside. You might say, Mike, a polygon's just a flat thing like a triangle, right? A triangle doesn't have an outside and an inside, a front side and a back side. And I say, sure it does. If I use these triangles to build myself a pyramid, there's going to be an outward-facing side of that triangle and an inward-facing side of that triangle. It's just the way it is. And you might say, well, but it doesn't matter what's outward and what's inward. It's going to matter a great deal when we get to what's called backface culling, where if you want your objects to look solid, you have to decide not to draw certain faces of your objects. And so, because we normally don't see the back of an object. We wouldn't, if we were looking at this in the real world, this line here would not be drawn. And in fact, drawing it makes it hard for some people to see that this is a pyramid, right? So in backface culling, you would not draw the back face. How are we going to tell if a front is a front face or a back face? That's future lectures. It's going to deal with things called surface normals. And if you want your surface normals to work right, you're going to have to define all of your polygons the same way as viewed from the outside. And the standard way, you could choose counterclockwise or you could choose clockwise. The standard way is to define your polygons clockwise when viewed from the outside. And if you do that, all of your surface normals for your forward-facing sides will point away from the, will point in the direction of visibility. Again, we're going to talk about all that later. Don't worry about it. I'm just saying that generally you have to define your polygons that make up your object consistently, and the standard way of doing that is to do it clockwise. So if we look at this front face, it's A, B1, B4, back to A. And I have it that way, A, B1, B4. And when you draw from the first vertex to the second vertex. then from the second vertex to the third vertex, from third to the fourth, from the fourth to the fifth, et cetera, until you get to the last vertex, and then you draw from the last vertex back to the first vertex. So you get the line A, B1, and you get the line B1, B4, B1, B4, and then you draw a last line from B4 back to A1, and that gives you your triangle. What about the back face? Well, the back face is A, B3, B2, A. Wait, Mike, you drew the front face as A, B1, B2, B4, A. That was going clockwise. You're drawing this back face as A, B3, B2. Aren't you going counterclockwise, Mike? Well, yeah, it looks counterclockwise here, but remember, we're looking at the back of that polygon. So in your mind, you have to move, and you get better at this with time, but in your mind, you have to move yourself to the other side of this polygon where you're looking at it from the front. And if you're looking at it from the front, the A, B3, B2 would again be in clockwise. So we're looking at the back of it. So A, B3, B2, A is counterclockwise, but we're looking at the back of it. So if I was looking at it from the front, that would be clockwise. Can you do that little thing in your head? Like I said, it becomes easier, but can you see what I'm saying? You have to draw your polygons in a way that you're defining them consistently, and we're choosing to do it clockwise, and so that means that it's clockwise when viewed from the outside, okay? So let's see about left. Left is A, B4, B3, A. So again, you can see that that's clockwise if I'm viewing it from over here. And then on the right side, it's A, B2, B1, back to A. So that's clockwise when viewing it from over here. So what about the bottom? Now I have to kind of imagine myself staring at the bottom of this thing. Again, if I'm looking at it from our perspective, it's B1, B2, B3, B4. You might say, Mike, that's counterclockwise. Well, yeah, but remember, we're actually on the back side of this bottom, right? We're above the bottom. So it looks counterclockwise from our current perspective, but if I were down here looking up at the base, you would see that this is in fact clockwise from that orientation. Vivian is asking an excellent question. Is there any specific determination that goes into choosing which vertex is the first point? It absolutely does not matter. The order matters, clockwise or counterclockwise, and doing things consistently, but I could just as easily have defined front. I defined it apex, B1, B4, apex, but I could have defined it B1, B4, apex, back to B1. Or I could have defined it as B4, apex, B1, back to B4. As long as the order, think about them in a cycle, as long as the cyclic order here is the same, it doesn't matter. I could start at A, B1, B4, I could start at B1, B4A, or I could start at B4A, B1. If you think about these things as being in a little circle, it doesn't matter where on the circle you start. Does that make sense? Okay, so an object is a collection, a 3D object, like a pyramid, is a collection of polygons, flat polygons. And each of those flat polygons is defined as a list of vertices, where we list the vertices in clockwise order when viewed from the outside. The final thing is the vertices. The vertices are just an unordered collection of points. It doesn't matter what order I keep them here, but we do have to have these vertices. And is having order consistent what's used to determine the front and back faces? Yes, Eric, that's exactly correct. And we've got a lot of we've got a lot of miles to go before we get to how you do that, but that is critical. If I define some of these faces clockwise and some of these faces anti-clockwise, you would be flipping some of your polygons over, so they would have back faces, and they would end up getting not drawn when they should be drawn, and vice versa. So that's why order is important. Now, you could define the system where everything was counterclockwise when viewed from the outside, but if you did that, you would then have to put a negative in front of your final calculation that would flip it. But if you go clockwise, your surface normals will point outward. Okay? And again, I haven't even talked about what a surface normal is, but the order is important. You can kind of think about it that way, Vivian. If the order of the vertices in a polygon appear to be going in counterclockwise order for you from your current viewpoint, then yeah, that's a back face that should be hidden. You can think of it that way. The math is going to be a little different from that, but that's at this point where we are right now, that's a good. You made a true statement. Okay. Okay, so a polygon may be rendered or drawn by drawing each of its polygons. That shouldn't say a polygon. That should say an object may be drawn by an object may be drawn by drawing each of its polygons. A polygon can be drawn by tracing lines from its first vertex to its second, from the second to its third, and so on, ending with a line from the final vertex back to the first vertex. Now notice something. If you're not getting rid of hidden faces, okay, if you're drawing every polygon in your object, each edge is going to be drawn twice for closed convex objects. So think about it. When I draw my front face here, right, I draw this edge, then this edge, and then this edge. But this edge is going to be drawn again when I draw, you know, Mr. Right side. And this edge is going to be drawn again when I draw Mr. Left side. And this edge is going to be drawn again when I draw Mr. Base. So every edge is actually drawn twice, which you're doubling your amount of work. Other ways around it, you can store polygons using what are called edge lists. You can go into your objects and you can try to, you know, not draw edges you've already drawn. But it gets complicated. Normally we just, the lines are drawn twice. But normally we do back face culling. So we throw out some of the faces, so not all the lines get drawn twice. But it is an inefficiency. I thought I would point it out so that the smart student wouldn't be sitting there left wondering, but am I not drawing all those lines twice? The answer is, yeah, you are. But it's cool. Okay. Yeah, that's basically it, Eric. Generally, it's just faster to draw it twice than try to keep track of what you need to draw and not need to draw. Okay. Perspective projection in my last 15 minutes. We started off talking about displays. We then started talking about polygons and how you store polygons. But somehow we have to move from computer graphics in a 3D world, right, to these flat display images. How do you do that? Well, the most common way that you use in computer graphics is something called perspective projection. And in fact, there are different kinds of projections, but when I drew my little pyramid here, this is actually a perspective projection that I drew it at. Because I have been saying over and over that the base here is square. But if you look carefully, I've actually drawn this right as a oh gosh, what do you call it? It's not a square. These edges are at a slight angle. This line is shorter than the trapezoid. Thank you. This line here is actually a little shorter than this line here. Well, why would that be the case? Well, in the natural world, things that are further away appear smaller. Okay? And so perspective projection, what it does is it captures that. So when something is closer, it's bigger. When it's further away, it's smaller. And again, you know, if you're looking at this from a distance, and it looks like it just went away, by the way, but if it doesn't come back, you can keep going with your own lecture notes. Like I said, all these lecture notes are on Moodle, and you should always have them up just in case my video drops, which it will do from time to time. But anyway, as I was saying, looking at this image here, I guess I need to go back into screen share mode. Looking at this image here, this line is actually a little bit smaller. If we were to be rendering this pyramid from closer, you know, if I move my nose closer to the screen, well, it doesn't change because it's fixed, right? But if you were doing head tracking and you wanted to make that thing look real, you would have to, as I moved my head in closer, you would have to change the perspective in which it was drawn. And so if you're really close to the front edge is a lot bigger than the back edge. So these things, it distorts more the closer you, the more the difference between the distance from me to the front face and me to the back face. If I'm, you know, a mile away, the difference in distance between the front of the pyramid and the back of the pyramid doesn't matter very much, and so they're almost exactly the same length. But if I'm, you know, such that, you know, the front face is twice as close as the back face, the front face is going to be a lot larger than the back face. Am I making some sense? Now, again, remember, it would be, the back face wouldn't be drawn, it would be hidden, but it affects the shape of these triangles here, right? Because this edge is not drawn vertically, it's drawn at an angle, and the same thing for this one. So this is what perspective projection does for you. It makes a representation that is that works in the same way your eye detects the real world, which is it makes objects that are further away smaller, and that gives you a realistic projection. There are other projection techniques, orthographic projection techniques, isometric projection techniques. If you look at some games, they kind of have a sort of a shifted at, like, you know, 33 degrees or 45-degree angle, and so it's kind of like a fake. When they're, you know, a lot of times if you're simulating a tabletop game or something like this, you see those kind of projections. Those are not perspective projections. You can look up the details of them if you're interested. It's just that perspective projection is the most natural projection, and it's used it's the most popular projection in computer graphics, especially if you're trying to get realism, and so that's the one that we covered. Okay. So one thing we have to talk about is, where is the viewer? If you're going to do a projection, the projection mathematically encodes where the viewer is at. Okay, it becomes part of the math. And you might say, well, I don't know where the viewer, how is the computer system going to know where the viewer's at unless it's got some sort of special sensor? And that's true. So what we do is we imagine a viewer at a point, and the point that we generally imagine the viewer to be at is somewhere in front of the projection screen, some distance d in front of the projection screen. So this is like the projection screen here, okay? And our objects, here's the point, a vertex of an object, exist out here in positive z space. We exist in negative z space. So if you're thinking about things, this is the real world. This center of projection, this is my eyeball, or it's modeled where my eyeball is. Now, obviously, I can move around and my eyeball won't always be there, but the graphics are rendered as if my eyeball is there, right? Staring at the center of the screen, some distance in front of this screen. And that allows me to project points, X, Y, Z points that have 3 dimensions onto the screen and get just an X and a Y position. So what I'm actually looking at here is I'm looking at the X, Y screen, but I'm looking at it in a top-down mode. I'm looking from positive Y down towards the origin. So this is looking down from above, okay? There's another perspective. This is a side perspective. Here I'm looking from positive X towards the origin. So this is still the XY screen, but I'm looking from positive X back to the origin. So what am I saying here? I'm saying we're modeling where the user's eyeball is. It's called the center of projection. I'm saying that all of our graphics, all of our imaginary world is going to exist beyond this magic window we call a screen or a display. And this magic world is in positive Z, the way we're representing it. The real world is over here in negative Z. So if I were to take this point and I were to move it over here, it wouldn't be visible anymore because it's no longer in the drawing space of positive Z. This is called, when you draw your objects in plus Z, this is called a left-handed system. A left-handed system. And it's called a left-handed system because if I take my left hand, you've got the y-axis that points up to positive. You've got the x-axis that points positive over here going to the right. And you've got this guy, which is the z-axis that points positive into the distance. I like the left-hand system because bigger z values are further away. There's an alternate system called a right-hand side system. In the right-hand side system, the z points towards you, so bigger z is closer. And that just seems weird to me. As things move further away, as the z gets bigger, I like my objects to move further away. So in this class, we use the left-hand sided system where positive z is where objects exist. Okay. All right. So this center of projection is also called the viewpoint. And here are the 3 equations that you need to be able to project vertices so you can draw them as dots on a screen. Let's say you've got a point, a vertex of a pyramid. So maybe it's the apex. That's the best way to think about this. Think about this point, XYZ, as a point of one of the vertices of our object. So think of it as A, the apex of the pyramid. So how should that A be drawn? Well, there's an X, Y, and Z for this point because it's a 3D point. And so what you do is you plug it into these equations. So X perspective projection is D, where D is the distance that you are in front of the screen. Units are arbitrary. You can choose what you want. So it's D times the X value from the point, from the 3D point XYZ, divided by D plus Z. That gives you the X perspective projection. That PS means perspective. Y perspective is very similar. It's the same D, right? times y over d plus c. So this gives you the drawable point xps, yps. We also keep around a zps, and you may say that that's weird because, Mike, you're converting to 2D, and in 2D I only have x and y. I don't have a z anymore. Yeah, but by doing this, it keeps around a relative measure of how far away that apex of the pyramid was from you. And that piece of information can be very useful if you're trying to figure out, well, is another object in front of that pyramid or behind that pyramid? So we need this, we will need in the future this depth information, and so that's the way you compute the z value. So where do these formulas come from? Did they just come from the air? No, they come from these drawings. And the definition of tangent. What's a tangent? A tangent, if you think about our center of projection, we have right triangles here, okay? Where this is the hypotenuse, this is the base, this is the opposite, right? So the tangent is the opposite over the adjacent. So one way of getting the tangent of this angle is this distance over d. Another way of getting that same tangent is x over d plus z. It's the same, it's by similar triangles. So x over d plus z has to give you exactly the same value as the projection of x onto this plane. This distance is x perspective projection over d. So that lets you figure out what this x perspective projection must be, because that relationship has to hold. So by tangent, x perspective projection over d must equal the original x over d plus z. Well, a little bit of algebra, you multiply both sides by d, and you get, oh, x perspective projection is d times x over d plus c. That's where it comes from. So that gave us the x. You compute the y perspective projection exactly the same way. Using this side view here, you can see that y perspective projection over d has to be the same thing as the original y over d plus c. They're both the tangent. They're both the tangent of this angle, the opposite over the adjacent. Does that make sense? Okay. So that's how you get, that's where these little formulas come from, is just from basic trigonometry. And what we're doing, remember, is we're taking these 3D objects and we are projecting them onto the display screen, which we're mathematically modeling as the XY plane where Z equals 0. So this plane, the XY plane where Z equals 0, is what we're going to actually map to our displays, our flat display device, right? That's how we're going to do that. Questions about that? Any questions about that? So what we end up with essentially is, here's my center of projection, here's an object. If you take all of the vertices and project them, right, you can get a flat image of this thing, and then you can just draw lines between those vertices that correspond to the polygons that you've already defined. And so you can actually be drawing these lines on a 2D screen, and you get exactly the same image as if you had projected all of the points along all of the edges. Okay? Questions? I think I'll answer your questions, Vivian and Eric, afterwards. So are there any other questions? I'm going to end today's lecture now because we're actually 1 minute over, and I will stick around and answer any questions, including these I see from Vivian and Eric. So I am going to stop the recording. Thank you guys for paying attention. We will continue on Friday.